Welcome to the Deep Dive. Today, we're tackling a connection that you might find really intriguing.
Yeah.
How our knack for spatial thinking, like figuring out directions or, visualizing shapes, ties into how well we do in math.
That's right.
You shared a fascinating review article with us, Navigating Spatial Ability for Mathematics Education, a review and roadmap.
Yeah.
And we're going to try and get to the bottom of why these, well, seemingly different skills are so linked.
Yeah, and what that means for how we learn and understand mathematics.
Exactly.
So in this deep dive, we're kind of on a mission, right? To uncover why those spatial skills, the ones that let you imagine, keep track of, and mentally manipulate shapes and locations, why they have such a strong, reliable connection to math performance.
Right.
We want to understand the different, let's say, flavors of spatial ability, the hurdles researchers face in defining and measuring them.
Which sounds like a big one.
Oh, it is.
Yeah.
And ultimately, how this knowledge can maybe give us a real edge in learning and, making sense of mathematics.
Yeah. Okay, so let's jump right in. This review article you sent over, it actually calls the whole area of spatial ability research a bit of a confusing terrain.
Mm-hmm.
It sounds like there's no single crystal clear agreement on what spatial ability is,
Yeah.
and definitely not on all the different pieces that make it up.
Exactly. The article pinpoints two major stumbling blocks for researchers. First off, the way spatial ability gets defined and broken down into smaller parts often feels, well, a bit like building on shaky ground. There isn't always a strong, solid theory backing it up.
Okay.
And second, there's just a massive collection of different tests and ways to measure these skills out there,
Right.
which makes it really tough to compare findings from different studies and get a clear picture of what we're actually looking at.
But even with all that complexity, the central idea keeps coming back, doesn't it? Our spatial skills, that ability to picture things in our minds, keep them straight, and even mentally move them around, is definitely connected to how good we are at math.
Yeah, absolutely. It's not something we're usually taught directly in school.
Yeah.
But some researchers think that if we actually focus on teaching spatial thinking, it could really boost how well we do in STEM science, technology, engineering, and math.
And here's where it gets really interesting.
It certainly does. The article gives some compelling examples of just how vital spatial ability seems to be across the whole spectrum of mathematics.
Like what?
Well, think about something as basic as understanding what numbers even mean. That can have a spatial side to it, like picturing a number line in your head.
Oh, okay.
Then, of course, there's geometry, which is obviously all about shapes and space. But the connection goes way beyond that,
Right.
stretching into algebra, where you might need to visualize relationships and how things change, all the way up to calculus. And even when you're trying to make sense of complex information presented visually, like in graphs or data visualizations,
So pretty broad then.
very broad. Even those big international PISA tests show a clear link between how well students do in math and their spatial thinking abilities.
And it's not just a vague feeling, like you said. The article shares some specific research that really made me sit up and pay attention.
Mm-hmm.
For instance, they talk about how first-grade girls with stronger spatial skills were more likely to use, well, smarter ways to solve arithmetic problems. But get this, those early spatial skills turned out to be the best predictors of their math reasoning abilities way later, when they were in 6th grade.
That's a really powerful finding, isn't it? Following students over time like that, it shows these early spatial talents aren't just important in the moment.
Right.
They actually seem to set the stage for their mathematical development down the road.
Wow.
And this isn't just a kid thing. The review also points to research with adults where different kinds of spatial skills were linked to different kinds of math problems.
Oh, interesting. How so?
Well, for example, the ability to mentally rotate objects was connected to questions about change and relationships. Spatial orientation that's more about knowing where you are in relation to things was tied to questions about amounts and quantities. And spatial visualization, which can involve more complex mental manipulations of shapes, that was linked to questions about space and form.
So it's not just one big blob of spatial ability that helps with all of math. Different spatial skills seem to have their own roles to play.
Precisely.
But this brings us back to the big question. How exactly are these things connected? The article mentions that while the link between spatial skills and math is pretty clear, the underlying reasons are still being explored.
That's a crucial point. Researchers are looking at several possibilities. One idea is that when we're doing spatial tasks and math tasks, similar areas of our brain might be getting activated. Brain imaging studies have shown some overlap there.
Okay, so shared neural pathways, maybe?
Potentially. Another thought is that there might be some basic thinking skills that are important for both. For instance, being
Hmm.
able to recognize shapes or understand how things scale, those could be helpful whether you're putting together a puzzle or understanding geometric concepts.
That makes sense.
Similarly, picturing the size of numbers on a number line uses a kind of spatial scaling, right?
Right, I see that. Okay, so the connection seems real. There are some interesting ideas about why. But let's dig deeper into that first challenge the article brought up. The difficulty in actually defining and breaking down spatial ability. It sounds like this has been a puzzle for a while.
It really has. Ever since researchers first started trying to understand spatial ability, they've wrestled with how to define it and what its core components are.
Hmm.
The article highlights that early on, a lot of research used what are called psychometric methods. Think of it like using tests and analyzing the results to try and identify different mental abilities.
Okay.
This led to lists of specific spatial subskills, things like closure flexibility,
Sure.
how easily you can see a whole object from incomplete parts, or
Sure.
field dependence, how much you're influenced by the surrounding visual field. They also looked at things like spatial relations, spatial orientation, spatial visualization, and speeded rotation.
Wow, that's quite a list. And it sounds like trying to nail these down wasn't so simple.
You're right. The article points out that trying to separate these different subskills often hit roadblocks because researchers were using different kinds of tests and different ways of analyzing the results.
So inconsistency.
Exactly. This lack of consistency meant that different research groups ended up with different labels for what might have been similar skills, and they developed different overall ways of thinking about spatial ability.
Yeah.
All this disagreement definitely makes it harder to get a clear picture of how spatial skills really connect to math. So it wasn't like they found one definitive list of spatial abilities that everyone agreed on.
So it's not like there's a universally accepted periodic table of spatial abilities.
Hmm.
It sounds more like different scientists have proposed their own ways of categorizing things.
Precisely. The article mentions some of the more recent and comprehensive attempts. For example, Yilmaz came up with an 8-factor model that tried to include skills we use in real-world situations, like navigating environments
Hmm.
and thinking about how things move in space and time. Then, Buckley and his colleagues proposed a very detailed model with 25 factors, and they even suggested there might be more.
25. That sounds incredibly detailed, almost too detailed.
Well, the article also raises that really good question. How useful are these huge lists for actually doing research?
Right.
That's a critical point. While these really detailed models might be interesting in theory, the sheer number of subskills makes it really challenging to study them effectively.
Yeah.
How do you design a study that can accurately measure and analyze so many different components?
Yeah. Seems impractical.
The article suggests that for research to really make a difference in how we understand learning, we need models that are a bit more, well, practical to work with.
That makes total sense. So instead of getting lost in these massive lists, the review article focuses on two key distinctions that they think are particularly important for understanding how spatial skills relate to math education research.
Hmm.
The first is the difference between spatial orientation and what they call rotational spatial visualization. Can you break that down for us in a simple way?
Absolutely. Both of these involve some kind of mental rotation, but the crucial difference is what you're imagining rotating.
Okay.
Spatial orientation, or what's often called perspective taking, is about imagining how a scene would look if you changed your position in space while the objects stay put.
Ah, like picturing the room from a different angle.
Exactly. Think about trying to picture what your living room would look like if you were standing in the doorway instead of sitting on the couch. Rotational spatial visualization, on the other hand, is about mentally rotating the objects themselves while your viewpoint stays the same.
Like turning a mug in your mind.
Perfect example. Imagine holding a coffee mug and turning it around in your mind to see all sides. The article points out that research suggests these are actually separate skills.
Really? How did they know?
Well, studies have found that people make different kinds of mistakes on tasks that measure these two abilities, and even different areas of the brain seem to be more active during each type of task.
Interesting. That example of imagining moving yourself versus rotating the object really makes it click. The article even mentions figures 2A and 2B from their paper, which, well, we can't see them, but the descriptions really help visualize this difference.
Right.
And the second key distinction they highlight is between mental rotation and non-rotational spatial visualization. This sounds like it builds on what we just talked about.
Yes, it does. The article discusses a 3-part framework proposed by Ramphal and his colleagues. In this framework, mental rotation is its own separate thing that's the image of physically turning an object in your mind, like figure 2B again.
Got it.
Spatial orientation is that perspective taking we just discussed, shown conceptually in figure 2A.
Okay.
And then the way they define spatial visualization here is about mental transformations of shapes that don't involve rotation or changing your viewpoint. Think about those paper folding puzzles.
Oh, yeah, those are tricky.
Right, where you have to imagine folding a piece of paper, punching a hole, and then unfolding it to see where the hole ends up conceptually. That's figure 2C.
Okay.
The article emphasizes that this kind of spatial visualization often involves thinking through a sequence of steps and relies on your ability to hold and manipulate spatial information in your working memory.
So it's more about sequences in memory.
Yeah, and it's connected to understanding things like symmetry, sliding shapes around geometric translations, and those flattened out patterns called nets that can be folded to create 3D objects.
So it sounds like Ramphal and his team are saying that spatial visualization is a broader category that includes these non-rotational transformations, and mental rotation is a specific type of spatial ability within that, or separate.
They frame them as three distinct factors: mental rotation, spatial orientation, and this non-rotational spatial visualization.
Okay, three factors. And the article makes a really important point that the specific choice of which of these skills researchers decide to study can actually lead to different findings and interpretations.
Absolutely.
They even mention a study from 2022 where whether they combined mental rotation and non-rotational spatial visualization into one measure or looked at them separately changed the conclusions they drew about their connection to math. That really shows you how crucial these definitions are.
It really does. If researchers are using different lenses to look at spatial ability, it's no wonder that the picture of its relationship with math can sometimes seem inconsistent. This really underscores why having clear and well-defined categories of spatial ability is so important for making progress.
This all makes the challenge of understanding this field very clear. But the article then shifts gears to talk about some broader ways of thinking about spatial ability, kind of stepping back from these very specific subskills. What are these broad factor structures all about?
Right, these are alternative ways of organizing spatial skills. They look at much wider categories, often based more on theoretical ideas about how we interact with space, rather than just statistical patterns from tests.
Okay.
The article brings up the distinction between large-scale and small-scale spatial abilities. Large scale refers to how we think about and navigate in larger environments, like finding our way through a building or using a map of a neighborhood.
Getting around town.
Exactly. Small-scale abilities, as we've been discussing, are more about mentally manipulating objects and shapes.
Right, the mental mug turning.
Precisely. And interestingly, a big review of lots of different studies actually supports this division, suggesting these are distinct enough to be considered separately.
Huh.
Some researchers propose that we might need different kinds of tests to really capture these two types things, like questionnaires about your sense of direction for large-scale abilities versus those mental rotation tasks for small-scale abilities.
So it's a difference between thinking about getting from A to B versus playing with a shape in your mind. That broader distinction makes a lot of intuitive sense.
It does.
And there's another broad framework mentioned in the article, this 2x2 classification by Newcomb and Shipley and Uddle and others, based on these two dimensions: intrinsic, extrinsic, and static dynamic. Can you explain what those mean?
Certainly. The first dimension, intrinsic versus extrinsic, is about where your mental focus is directed. Intrinsic spatial skills involve focusing on the spatial properties of a single object, its shape, its parts, how they relate.
Okay, object-focused.
Right. Extrinsic spatial skills, on the other hand, are more about the spatial relationships between different objects in a scene.
Scene-focused, got it. And static dynamic.
Static tasks involve looking at and thinking about objects and their spatial relationships as they are, without any movement or change. Dynamic tasks go a step further and require you to imagine spatial transformations, like movement or rotation, of one or more objects.
Okay, so if we mix and match these two dimensions, we end up with 4 categories. What kinds of tasks would fit into each?
The article gives some good examples, which helps. The embedded figures test, where you have to pick out a simple shape hidden within a more complex design that's conceptually figure 3A, is an example of intrinsic static. You're focused on the parts of a single, unchanging shape.
Okay.
Paper folding and form board tests, like Figure 3B, where you imagine folding paper or fitting pieces together, would be intrinsic dynamic because they involve mentally transforming a single object.
Makes sense.
Water level tasks, where you have to imagine how water would look in the Silton container that's Figure 3C, are extrinsic static. You're looking at the relationship between the water and the container, but nothing is actually moving.
Right.
And the Guilford-Zimmerman spatial orientation task Figure 3D conceptually, which involves understanding viewpoints in space, is an example of extrinsic dynamic because it requires you to imagine a change in spatial relationships between yourself and other objects.
That 2x2 framework seems like a really useful way to categorize things. But the article also points out that there's been some debate about how well this framework holds up in research, specifically mentioning a study with children in 2018 that didn't find strong evidence for that static dynamic distinction.
That's an important piece of the puzzle. While the 2x2 framework offers a neat sort of theoretical way to think about different kinds of spatial skills, the research, especially with younger learners, hasn't always strongly supported that static versus dynamic split.
Interesting.
It suggests that our theoretical ways of categorizing things might not always perfectly match how these skills actually work in practice, or at least how they develop.
Yeah.
The article also notes that we don't really have many well-validated tests that were specifically designed to measure these broader categories. Instead, researchers often try to fit existing tests, which were usually created to measure those more specific subskills, into these broader boxes.
So these broad factor approaches offer a different lens, but they come with their own set of challenges and measurement issues.
Exactly.
And then the article moves on to this completely different idea of a single underlying spatial ability, a unitary factor structure. This sounds like a real shift in perspective.
It is. Instead of thinking about spatial ability as a collection of separate skills, the unitary factor view suggests that there might be one fundamental common ability that influences how well we perform on all different kinds of spatial tasks.
One G factor for space, almost.
Sort of, yeah, but separate from general intelligence G. This idea gets some support from genetics research, including studies with twins, and from brain imaging studies that have found evidence for shared genetic factors and brain activity patterns across various spatial tasks. A study by Malinchini and colleagues in 2020, for example, found that a statistical model that assumed a single underlying spatial ability actually fit their data the best, even when they took general intelligence into account.
That's fascinating. So it's like there's a core spatial intelligence that influences how well we do on everything from mentally rotating an object to finding our way around a new city.
That's the idea.
What would be the benefit of thinking about it this way?
Well, the article suggests that thinking of spatial ability as a single, unified thing could be really helpful when we're looking at the general relationship between math and spatial skills. If you just want to know if there's a broad link, or maybe if you're using spatial ability as a general factor to control for in your research.
Right, as a covariate.
Exactly. Then the simpler model might be enough. However, and this is a big however, the article also points out a significant limitation. We don't currently have really good, reliable tests that are specifically designed to measure the single, overarching spatial ability.
So researchers who lean towards this unitary view often end up using...
They end up using the same tests that measure those more specific subskills we talked about earlier. They might combine scores or something.
So it's a bit of a theoretical simplification, but the tools to measure it directly aren't quite there yet.
Pretty much.
This brings us to the second major challenge the article highlighted. The sheer number of different spatial assessments that are out there. It really sounds like choosing the right tools is critical.
Absolutely critical. With so many different ways to define and categorize spatial ability, it's really crucial for researchers to carefully select the specific tests and questionnaires they use.
Yeah.
The choice of measurement tool needs to line up with their particular research questions, the specific spatial skills they're interested in, and of course, the age group they're studying.
Right.
The article mentions the Spatial Intelligence and Learning Center website, spatiallearning.org, as a helpful place to start exploring some of these measures. But they also acknowledge that we still need a more user-friendly and comprehensive guide to all the available instruments.
And to help with this, the review article itself includes a table, Table 1, that actually links different spatial ability tests to specific subcomponents and the groups of people they were designed for. That sounds like a really valuable resource.
It is, and looking at that table reveals some interesting patterns. For example, you can see that a lot of the Tests currently used were originally developed for things like military recruitment or assessing job suitability.
Oh, really?
Yeah, and they were later adapted for use with students. It also highlights that certain types of spatial skills, like mental rotation and spatial visualization, are measured much more frequently than others.
So we test those a lot.
We do. While some areas, especially those extrinsic static abilities we talked about in the 2 by 2 framework, like the water level task idea, have fewer dedicated tests.
And what about for kids?
There's also a clear need for more tests that are specifically designed for children. Many were designed for adults initially.
So it's not just about grabbing any spatial test. It's about finding one that truly measures the specific skill you're interested in and is appropriate for the people you're studying. The article then zooms in on 3 main groups of tasks that they see as particularly relevant to understanding the link between spatial ability and math, drawing on those specific subskill distinctions and aligning with that 3-part framework we discussed earlier. The first of these is spatial orientation tasks. What do these typically involve again?
Right, spatial orientation, understanding your position and perspective relative to objects. Tasks measuring this often involve things like understanding scale, reading maps, identifying what an object would look like from a different viewpoint, and determining position and location.
Oh, okay.
The article mentions that these skills have been linked to how well children do in early arithmetic and with their problem-solving strategies.
And the tests for this?
Well, one of the older ones was the Guilford-Zimmerman spatial orientation test, but it got criticized for being quite complex, maybe measuring more than just orientation. More recently, the object perspective spatial orientation test developed by Hegarty and Waller, conceptually Figure 2A, was designed to be a more focused measure of just that ability to imagine changes in perspective.
More targeted.
Yeah. And there are also simpler versions of these kinds of tasks used with younger children, like those found in the Spatial Reasoning Instrument, or SRI.
Okay, that makes sense. The second category is non-rotational spatial visualization tasks. We used paper folding as an example before, but what are some other types of tasks that fall into this group?
Right. These tasks, like the name suggests, involve mental manipulations of shapes and spatial relationships that don't require you to mentally rotate an object.
Okay.
They might involve things like understanding reflections, thinking about visual patterns in geometry, recognizing symmetry, comparing symbolic representations spatially, and imagining the overall layout of a problem.
So manipulating shapes without turning them?
Kind of, yeah. The article highlights 3 tests from a well-known set: the paper folding test, Figure 2C, the form board test, where you pick pieces to make a shape, and the surface development test, matching flattened nets to 3D forms. However, it's worth noting that even with these non-rotational tasks, some clever people might still use mental rotation strategies to solve them.
Oh, okay, fair enough.
And tasks like the embedded figures test, Figure 3A, where you find a simple shape in a complex picture, also fall into this category, measuring your ability to mentally pull apart a visual scene.
So these tasks tap into our ability to mentally manipulate shapes and understand their relationships without necessarily turning them around in our minds. And the third category is mental rotation tasks, which we've already talked about a bit. These seem to be a pretty popular area of study.
They are indeed. Mental rotation, that mental operation of turning a mental image in your mind, has been linked to a really wide range of mathematical skills, from basic calculation and arithmetic all the way to geometry and more complex problem solving.
Seems quite fundamental.
It appears to be. The ability to do this seems to develop quite early, usually between ages 3 and 5, but there are noticeable individual differences.
And the gender difference question.
Yeah, you might have heard about gender differences in performance on these tasks. The article does mention them, but also points out that these differences might be partly due to cultural and social factors, not purely biological.
Okay. And the tests themselves.
They can use either 3-dimensional objects, like the classic Shepard and Metzler figures, that's Figure 2B, or tests like the Purdue Spatial Visualization Test, rotations and the mental rotation test.
Right.
Or they can use 2-dimensional shapes, as in the card rotation test and the picture rotation test.
So 2D or 3D rotation.
Exactly. But again, a small caveat. Some researchers have raised concerns that certain questions in some mental rotation tests might actually be solvable using strategies that don't involve true mental rotation.
It really highlights how tricky it is to isolate and measure these specific spatial abilities.
It absolutely is.
And given all these different ways of categorizing spatial skills and the huge number of tests available, the article provides a framework to help researchers make more informed choices. Can you walk us through this guiding framework? It sounds useful.
Absolutely. The article offers a flowchart, conceptually figure 4, as a kind of practical guide for researchers. It helps them connect their chosen way of thinking about spatial ability, their taxonomy, with how they plan to analyze their data.
Okay, so what's the first step?
The first question in the flowchart asks whether spatial ability is being used basically as something they're controlling for in their study, a covariate, or if it's the main thing they're interested in studying.
Okay, and if it's just a covariate?
If it's just something they're controlling for, the recommendation is to use that unitary model, the idea of a single underlying spatial ability, and to get a broad measure by combining scores from several different specific spatial ability tests, like maybe using the SRI composite score.
That makes sense. If you're just trying to account for spatial ability generally, a broad measure is probably sufficient. What if spatial ability is the main focus?
Then the next question the framework asks is whether the researcher is interested in spatial ability as a general concept or in specific subcomponents like mental rotation or spatial orientation. If they're looking at the overall role of spatial ability in relation to, say, a particular area of math, the article again suggests using the unitary model and a combined score across different measures.
Still the general approach.
Right. But if they want to really dig into the role of one or more specific subskills, then they recommend using those more detailed classifications we talked about earlier, like Ramphul's three-factor model or the specific visualization and rotation types.
Okay, getting more specific now.
Exactly. And the framework goes a step further, asking whether the study will focus on just one specific subskill or multiple ones.
And how does that guide the analytical approach?
Well, if the research is centered on a single spatial subskill, the suggestion is pretty straightforward. Use a single score from a test that is known to specifically measure that skill.
Makes sense.
If the study is looking at multiple different subskills, then you would aim to get a separate score for each of those subskills using dedicated tests for each.
One score per skill.
Precisely. And finally, the framework touches on how to choose the right tests, reminding researchers to think about relevance. How relevant are the specific skills to their research question? The age of the participants, and any practical limitations like testing time.
Practicalities matter.
They do. And they also point back to that table 1 in the article as a helpful starting point for identifying appropriate tests.
It sounds like a really practical tool that acknowledges that researchers have different goals and limitations.
It tries to be, yeah.
And the article does end with an important reminder, right? That math problems can often be solved in many different ways.
That's a crucial point to keep in mind.
So findings about the link between a specific spatial skill and a particular math task might not necessarily apply to all students or all types of problems.
Exactly. The relationship between spatial ability and math is intricate, it's complex, and the fact that individuals approach and solve problems in different ways is always going to play a role.
So to bring it all together then, it's pretty clear that how well we can think spatially plays a significant role in our ability to understand and do well in math.
It definitely seems that way.
But as we've explored, actually defining what we mean by spatial ability and figuring out how to best measure it is a surprisingly complex challenge. There are lots of different ideas and tools out there.
It's a crowded field.
The review article you shared really shines a light on these complexities, though, and provides what seems like a valuable roadmap for researchers trying to navigate this area.
Exactly. The article really drives home those two central hurdles. The lack of a single universally accepted way to define spatial ability and its parts, and just the sheer abundance of different tests we can use.
Right.
The author's main contribution, I think, is giving researchers a guide, that framework, to help them make more informed decisions about which taxonomies and which tests will be most useful for answering their specific questions about mathematics education.
And they also point out some areas where we still have limitations and where future research needs to go, don't they?
They do. Things like updating our tests to work better online, which is obviously important now. Doing more large-scale studies that link specific spatial abilities to specific areas of math learning. Developing more tests that are designed specifically for children. Getting more detailed information, process-level data about how people actually solve these spatial tasks in their minds.
Like what strategies are they using?
Exactly. Creating more tests for those less studied areas like extrinsic static abilities, and continuing to explore the validity of models like that unitary one. It sounds like there's still a lot to uncover.
A lot of work still to do.
There certainly is. The authors emphasize that our understanding of the structure of spatial ability is at a really interesting and potentially important point. These are skills that can likely be developed, right?
That's the hope.
And that could have a real impact on how we design teaching methods and assessments in STEM fields. By continuing to investigate these connections, we can hopefully gain a deeper understanding of how we learn and develop more effective ways to support students.
This has been a truly eye-opening deep dive into a topic that I have to admit I hadn't fully appreciated before. It really makes you wonder about those hidden skills that might be quietly influencing our ability to grasp abstract mathematical ideas. And on that note, here's a final thought for you, our listener. Considering this intricate relationship between how we perceive and manipulate space and our ability to grasp abstract mathematical concepts, what everyday activities or learning approaches might inadvertently be strengthening or maybe weakening these crucial spatial foundations for your own mathematical understanding?
Yeah, something to think about.
It's definitely something to think about. Thanks for joining us on the Deep Dive.